friends, welcome to our YouTube channel Design in Video, where we help students to learn and understand design concepts in a more simple and systematic way. Today we'll solve first numerical in Design of Machine Elements DME-1, Module 1, Design for Static Strength. The problem is like this. A beam of rectangular uniform cross-section is fixed at one end and carries a load of 1000 Newton at a distance of 300 mm from the fixed end. The maximum bending stress in the beam is 80 Newton per mm square. Find the width and depth of the beam if depth is twice that of width. So first we'll write the data. It's a cantilever beam of uniform rectangular cross section. The load F is given as 1000 Newton. The length of the specimen, it is given as span. I can say the span of the specimen is given as L is equal to 300 mm. The bending stress sigma B is given as 80 Newton per mm square. Here he wants to determine the width, so therefore width B is equal to question mark, depth H is equal to question mark, and given condition, very important, the condition is H is equal to twice the width, that is depth is twice the width. So we will be using this condition for solving the numerical. So first we should be knowing the bending moment equation. So let me write. We know that bending moment equation is given by this equation: MB over I is equal to sigma B by C is equal to E by R. In this complete equation, we will not be using this capital E, the Young's modulus of the material, and radius of curvature, as it is not given. So instead we will be using we'll be more focusing on MB, I, sigma B and C. We'll try to see what are those terms one by one. First, let me find the bending moment. Bending moment MB. So refer the data handbook here. So there is chapter 2, static stresses in machine elements by Dr. K. Lingaya, volume 1. The table to be referred is 2.8. So here, since it is a cantilever beam, you can see this is a cantilever beam, the end loaded, and the equation to be used is MB max is equal to F into L at location B. So that is the bending moment. So here the bending moment MB is equal to force into perpendicular distance. So force, it is given as 1000 newtons into distance is 300 mm, so it comes to be 3 into 10 to the power 5 Newton mm. That is your total bending moment MB. Next we will move ahead to calculate the moment of inertia. Let me separate these two things. Here, moment of inertia, capital I. To find this, refer the table 2.7 from same data handbook, Dr. K. Lingaya, Volume 1, table number 2.7. Since it is a rectangular cross section, the moment of inertia is given by bh by 12. So the moment of inertia I, it is given by bh by 12. Refer table 2.7, volume 1. Here refer table 2.8, volume 1. I is equal to b, h is given as a condition of 2 times b, so we will be using that condition, 2b cube by 12. So here the moment of inertia in terms of b, it will be 0.667 b to the power 4. So this will be my net moment of inertia, 0.667 b to the power 4. Next, let me find the distance of CA from the extreme fiber. Distance of C in total axis from the extreme fiber, that is distance C. So C is given by d by h by 2. So what is this C here? So suppose you have a rectangular cross section, so this is the rectangular cross section, and the h is given, that is the depth is given h, and here the width is given as b. If I take the central axis which is passing through the h, and this distance from the extreme fiber is c, and this is my axis, central axis CA. So therefore C can be written as h by 2, but we know the condition h is equal to 2 times b by 2, so 2 get cancels, so left with c is equal to b. So I am aware of all the terms in this equation one by one. I got MB, I got I got sigma b, I got c. Now I can rearrange the equation such a way that I can have left on the LHS the sigma b. So therefore, rearranging the above equation, rearranging the bending equation, sigma b is equal to mb over I into c. mb we know it is 3 into 10 to the power 5, by I it is 0.667 b to the power 4, and c is b. So here if I cancel out the terms b and b, here I am left with b cube. So if I can solve for b, so therefore sigma b is given as 80 Newton per mm square, so therefore solve for b using the calculator. I can get b is equal to 17.78 mm, which can be approximated to 18 mm. So therefore the width b is equal to 18 mm, and the depth h is equal to twice the width. So therefore I can write the depth h is equal to 36 mm. So these are the dimensions of cross section. Thank you one and all. Thank you for watching our video.